Sit on the little one.
Today we're going to focus on solution concentration. The last couple of days we've just been focusing on what is the nature of solutions in general. In this class, a lot of times, as you guys know, you'll be provided with materials that are in liquid form. They're solutions, and so that means they're made from dissolving certain things in some water, in this class generally just water. But we need to keep track of how much stuff was dissolved in there because, as you know, you can make solutions that are more or less concentrated. So we need to figure out the quantitative aspects of this. The first one that we're going to look at, we're going to look at three main ones this year. I might throw in a fourth, is molarity. We've already looked at molarity this year. I threw it in order to help us do a lab. It's a fairly easy concept. You guys seem to grasp it pretty well. If you remember, the symbol for molarity is a capital M. If it's in print, that will be italicized. I don't know how to do italics when I'm writing on the board, so yeah. Anyway, if you remember, and you may not, molarity is moles of solute per liter of solution, which we can write in a handy little equation that looks like this. Okay, moles over volume. Just like the ideal gas law, you have to remember that our volumes are going to have to be in liters. We shouldn't have any problem with converting because we did that for, nearly a week. So we should be in pretty good shape there. Let me see. One of the handy things about this equation is we have, once again, another way to convert to moles. What would moles be equivalent to in this case? Molarity times volume. We're about to say molarity over volume, right? But remember this volume, which is currently in the denominator, we need to move to the other side in the numerator, right? There you go. We're just going to do this off to the side a little bit. This is not necessarily included in what we're doing. We now have a number of ways of converting to moles for nearly every kind of state of matter. For example, if I have a solid, how do we convert to moles if I have a solid? Like, for example, sodium chloride, calcium carbonate. How do I convert to moles if I know the...
You add you find the mass.
Yeah, you use the molar mass, okay? You start with the mass, the grams, and use the molar mass. What if I have a gas? How do I convert to moles with a substance that's in the gaseous state? There's actually two answers to this question.
You could divide by 22.42.
Use the molar volume if there's a condition there.
If STP.
Yeah, for STP. So a gas at STP, use molar volume. Which, as someone said earlier, is 22.42 liters per mole. What if we're at non-standard conditions?
Well, if you can convert.
Right? What if we have a solution? How can I convert to moles? Use the molarity equation. And And what if I have a liquid? Now, this one's going to take a little thought on your part. How can I get to moles of a substance? For example, what if I wanted to know the number of moles of an alcohol? Go ahead.
Would it be molar volume?
No, because what is the molar volume used for?
Gases.
Which are dependent on temperature and pressure. Whereas the volume of a liquid is not dependent on temperature and pressure enough to make a difference. How can I get to moles? Yes? Molar mass, and what else? Because how do we measure liquids? What unit do we typically measure liquids in? Volume, right? Milliliters. So, see, I'm not like you guys. My phone goes off, I don't go. So how do we get to molar mass?
Turn to like milliliters.
How, well, we're already in milliliters.
Oh.
What's D?
Density.
Density. Yeah. So we can use the density to convert to grams, which we can then convert to moles. Anyway, so we now have a method to get to moles from every, really typically every state of matter that you're going to encounter this year. All right, moving on. A couple of examples of using molarity. I've already given you 2 or 3 back when we used this earlier, but I'm going to do it again. Determine the molarity of a solution prepared by dissolving 72.3 grams of ammonium chloride in enough water to make 250 milliliters of solution. All right, so we're looking for molarity. Obviously, this is the equation which we're going to use. Do I have either one of these pieces available?
The volumes.
We have the volume, but is it in liters?
No, it's a milliliter.
No, so the first thing you're going to have to do is convert that volume to liters by one of 2 methods that you guys might use. Divide by 1,000, or same result, move the decimal point 3 places to the, see, that's the thing. That's why I always like to think of divided by 1,000, because you guys are never sure which way to move the decimal point sometimes, right? So divide by 1,000. You know, the other way to look at it is convert, which ultimately ends up being divide by 1,000, but still. Anyway, so we have the volume. Now, how am I going to get to moles?
Don't you,
Well, obviously it's a solid. It's in grams. I just talked about how we do that. We use the molar mass. Well, in order to use the molar mass, we have to be we have to know what it is. What is the formula for ammonium chloride? NH4. Do you remember the charge on that?
1.
Yep, 1 plus. Chloride, we already know. Cl with A. 1 negative, they cancel, so there we go. Now we just need to know its molar mass. What's the mass of nitrogen? 14.01. Each hydrogen is 1.01, so we're up to 18.05 so far. Plus chlorine, 35.45. Oh, I see how it works. If your electronic device is not your phone, you don't want to touch it. Ah, good, Michaela. She got my hint. Of course, so did 17 others of you just decided to.
53.50.
35.45 plus 18.05. What is it?
53.49.
For some reason I think it was 50, but okay. I'll wait till Michaela gets it.
I got 53.5.
Yeah, that's what it is, 50. Okay, so anyway, if you look at this, 72 divided by 53, that's real close to 1.5. 1.5 times 4 is going to be really close to 6, so a little under 6. Well, I get 5.41. Now, we would write the capital M. You may remember this from earlier conversations this year. If I were to ask, say, Wes, hey Wes, what is the answer to this problem? He would say, oh, well, Mr. Lehman, it's 5.41 molar. You guys remember using that term before? Okay. So that means we would create a solution that is 5.41 molar solution. That's fairly highly concentrated, as it turns out. Okay, next, another example. Actually, it's a very practical example from my point of view. Because this is what I have to do a lot of times when I have to prepare some solutions for labs for you guys. For a lab, 500, I've determined that 500.0 milliliters of a 1.24 molar glucose solution. Does anyone remember the formula for glucose? And all year long, when I've been asking you guys for the solution for, or for the formula for sucrose, you guys have been trying to give me the solution or the formula for glucose. So that thing you've been saying wrong all year, now would be the time to say it. See what? Yep. Eric. As someone said, slow, a little carried away there. C6H12O6. Anyway, for a lab, I need 500 milliliters of 1.24 molar glucose solution. Is required. Describe. How to prepare the solution. So how'd it go? Eric, I'm going to highly suggest you not sit there. You know why. Anywhere other than, I mean, you've been around for like an hour now. You kind of know where not to go. You were here for 2 of them, is that right? Apparently Derek used to be bite. All right, anyway, moving on. This is incredibly typical to what I have to do. As you guys have known all year long, where'd that go? Oh, I put it back. We've been using solutions that I've prepared for you, right? And they almost always have the capital M, molarity, on there. Okay? So what I do is I sit there and say, okay, I'm going to do this lab. I need this concentration of stuff. Each group is going to need certain X volume, whatever that happens to be. So I multiply that volume by the number of groups I have. I always pad it by half a liter to a liter because you guys are going to screw up. That's okay. We anticipate this, all right? And so then I decide, oh, I need 500 milliliters of this solution. How do I go back there and make that? Is the question. Okay, what do I have to do? Well, we're given a volume and a molarity. Now, what state of matter do you think the glucose is? What's that?
Liquid.
It's a sugar, so it can be a liquid. If you've got K-Rose, anybody have K-Rose syrup at home? You guys ever use that or see that? Okay, that's glucose, except it's highly, highly concentrated glucose. But anyway, it's a solid. Okay, I've got it back here as a solid. So, since it's a solid, I'm going to have to convert that to moles using the molar mass. Okay, so I'm going to have to measure out a mass of glucose. So when you're doing one of these types of questions, there's two parts to the question. Step one is the math piece. How much glucose do I need to measure out? How am I going to find that? Well, once again, molarity equals moles over volume. Ultimately, I need moles, which I can then convert to grams using the molar mass. So, I'm going to take the molarity, which is 1.24 molar, multiply by the volume, which is 0.5000 liters. And then that's going to give me, well, half of 1.24. Somebody do that in your head real quick. Don't touch your calculator.
Half of 1.24.
Yep. Half of 1.24. 0.62. Right? What, are you amazed by that?
Yeah.
Divide this by 2.
Oh, I thought one. Never mind.
You're with me, right?
Yeah.
Okay.
See, I
Okay.
read 2.4 and I was like, how'd you get 6?
You thought I was rubbing off on him or what?
Yeah, I was like, what?
That's funny. Anyway, moving on. So now we got 0.62 moles of the glucose, but we need to convert that to. Okay, could somebody go measure out 0.62 moles of glucose?
90 milliliters.
No, you can't. We need the molar mass to convert it to grams. How many carbons?
6.
Which is, what's the mass of carbon? 12.01. How many hydrogens? 12. So we're talking 7206 plus 12.12 plus 6 times 16, which is 96. Add all those up. I actually happen to know this because I use it a lot.
It was 180.18.
Yep. I don't know how many moles that is. Half is going to be 90
Yeah, 111.
plus another 18, 118.
I got 111.7116.
111.7 grams. which is actually one extra significant figure, but that's okay. Now, ooh, I know what I did with that. Step 2 is actually preparing the solution. Step 1 was the math. We had to figure out how much of the glucose we actually need, okay? Part 2 is the actual preparing. Ashley, since you haven't been here, what is this? Dextrose, otherwise known as glucose. Here we go, glucose. Now, I need 111.7 grams of glucose. How am I going to obtain that? Well, here's a little interesting discussion. You guys know how to use a balance, right? But here's the thing. How many significant figures do I really need? Just 3, okay? If you remember, the balances that you guys have been using all year go out to the thousandths place. So anything that I weigh or take the mass of that's over 1 gram is going to actually have a minimum of 4 significant figures. You guys following? So I really don't need to use a balance as good as the ones you guys have been using. That's way more precise than I actually need. I only need 3 significant figures. And since I'm looking for 111, almost 112 grams, there's the 3 right there that I need. Does that make any sense? So technically, I only need a balance that's only precise to what decimal place? The ones place. That's it. That's all I need. Which you can buy a billion of those balances. Those things are cheap. Okay? Because you don't need that many decimal places. The ones you guys have been using all year long are way more than what we need for this particular case. So anyway, a lot of times what I'll do is I'll use an electronic balance that doesn't have the precision that the ones you guys have been using. I think I taught you guys how to use these earlier this year also, right? So all I would do is take my little weighing boat, that's why these things exist, put that on the balance. Do you remember what to do now? Zero it out, add my 112, 111 grams of the glucose. Okay, there we go. Got that in there. Awesome. Okay. Now, here's the beauty of these trays. I know you guys have used these before, but you'll see why these are nice. Now, remember, I'm making 250 milliliters of solution. The solution is both the solute and the solvent. Does anyone remember what this device is called? It is not an Erlenmeyer flask. This is an Erlenmeyer flask. It is not a Florence flask, although it can be confused with a Florence. A Florence has no graduation, where this has 1 mark all the way around here. What quantity could this be used to measure? I'm trying to give you a hint here. What are we going to measure with a flask? Mass? Temperature? Volume. What's the name of this? Volumetric flask. You guys remember that now? Okay. Now, each of these volumetric flasks, like I said before, is very precisely made. This one in particular is a 500 milliliter volumetric flask. Hey, 500 milliliters. If the liquid comes up to this line right there, it's exactly 500 milliliters. Okay? So what should I do? Put 500 milliliters of water in here and then dump in the sugar?
Dump it in and then put 500.
Why don't I do it the first way? It'll go up above 500 milliliters. We want 500 milliliters of solution, both pieces, right? So this next part, I'm going to describe to you what to do. Do not write it down the first time I say it. Just listen to what I'm saying. I'll say it 2 or 3 more times. Then you can write it down, okay? But try to understand what I'm trying to tell you. What we're going to do is once we've got the flask and we've got the material weighed out, I'm going to fill this about halfway up with deionized water. So I'm going to fill the flask about halfway up with the ionized water. Then, I don't have any. Let's imagine I'm using the ionized water. Okay, about halfway up. Then what I'm going to do is carefully add the sugar, the glucose, and that's why this is the whole point of these weighing trays. Notice how I can bend it and make it like into a little funnel. Add it very carefully. Now, you guys ever pour things out of these and it sticks to the sides? You take your little water bottle and make sure every last bit of that ends up in there. Okay? So now I've added the solid. At this point, mix. Okay? Get it all mixed up. It's a lot easier to mix it up when it's not full. Okay? Now that I've got it all mixed up, what am I going to do?
Add the rest of the water.
Add the rest of the water, fill to the line is the way I like to say it. Fill with water to the line. I would highly suggest at that point in time, once you've done that, okay, I did this very quickly, okay, is remix. Okay, and there's the description. So, I'll repeat that whole process. Fill the flask halfway, the ionized water. Add the solute. Mix. Fill with water to the line. Mix again. I'll repeat. Fill the flask halfway with water.
This would be step 2.
This is all step 2. Add the solute. Mix. Fill to the line with more water. Mix again. It's a pretty simple process if you think it through. Ben, how's it going over there?
Fine.
A little nervous?
That one kind of made my ear ring.
Really?
Yeah.
Oh, these are nothing.
They get loud. What's exactly happening?
It's a contact explosive, and a lot of times just air currents are enough to cause it to go off. 2 happened while Eric was taking his test, I think, didn't it? All right. Moving on. And again, this is a very practical thing. This is what I do every time I make a solution for you guys for class. We are currently done with molarity. There are more different types of ways to express solution concentration. The next one we're going to look at is called molality. Very similar to the word molarity, but it's called molality. This one is abbreviated with a a lowercase m. In print, that's also going to be italicized. I don't know how to do that on paper. Now, molality is moles of solute per kilogram of solvent. Per kilogram of solvent. A couple comments I want to make about molality before we move on. Molality is temperature independent. That was about a 1/4 of a bang.
Are you serious?
Temperature independent. Now, you may be wondering, well, who cares? Why do I care? Molarity is temperature dependent because, if you recall, I don't know if I described this to you way back in August. A lot of our glassware is calibrated to a specific temperature. You guys remember talking about that? Does anyone remember what that temperature was? Well, Fahrenheit, it's actually 68 Fahrenheit. It's 20 degrees Celsius. All this stuff's calibrated at 20 degrees Celsius. Why do we care with volume? What's going to happen if I make a solution at 20 degrees Celsius that fills up to the line, and then I put this in a room that's warmer? It's going to expand, because things have a tendency to expand when they're warmer, most things, right? So now, think this through. This will tell me how your brain works. If I did exactly that, maybe I made I forget what that turned out to be, was it 5.41 molar solution? Okay. Let's say I made a 5.41 molar solution of glucose at 20 degrees Celsius, and then put this 68 degrees Fahrenheit, and then took this into a room that was 75 degrees Fahrenheit, about 23, 24 degrees Celsius. What's going to happen to the volume? It's going to get larger. What's going to happen to the concentration? It's going to what? It's definitely going to change, because what happened to the volume? It got bigger, so it will decrease because it's an inverse relationship, right? So every time I pour a little bit out, I'm not getting as much of the solute as I think I'm getting. You see where I'm going with that? So this a molarity is temperature dependent. Molality, on the other hand, what happens to the mass of a solvent as the temperature changes? Absolutely nothing. The mass is the mass is the mass, right? The volume might change, but the mass is not. So this is a temperature independent concentration expression, a lot of times used for colligative property calculations. You don't know what colligative properties are yet. You will find out tomorrow. Anyway, handy dandy little equation, you can use that. Actually, it's almost exactly that. You can say molality equals moles per kilogram of solvent. Not much of an equation, but there it is, okay? Example. Determine the molality of a solution prepared or from 137.2 grams of potassium iodide in 280.0 milliliters of water. There it is. Stuff's drying now, isn't it? What's happening with the bottom of it? Hey, cover up your ears. Anyway, hold on. This one's got a chance. Looks like something over there. These are wimpy. They do a very good job this year. They were bad. I don't know why. No, I'm sorry. That's all right. anyway, here we go. Now, we're looking for molality. Molality is moles of solute per kilogram of solvent. I'll just continue from here. I need the moles of the solute. I currently have the mass, so I'm going to have to convert that to moles. So we take 137.2 grams of potassium iodide. Potassium, if you recall, has an atomic mass of 39.1. Iodine has a mass of 126.9. You add all those things up, it should come up to 166.0. Some of you have done that already. Okay, now, all we need is the mass of the solvent. Well, what is a solvent? Water. But it's 280 milliliters. What is the mass of 280 milliliters of water? Okay, what other information are we going to need to know about the water to find its mass? We know its volume. Not yet. No. I already gave you the hint earlier, people, today. You need to know its density. Does anyone remember the density of water? 1 gram per milliliter. So if I have 280 milliliters, I therefore have 280 grams, which then I convert to kilograms by dividing by 1,000, right? So here we go. Now, some of you are okay with doing that in your head. I'm just going to go ahead and do it this way. For those of you that prefer to see that, ends up being 0.2800 kilograms. .9. A little over 3 point something. Anybody have it? Michaela, what do you have? 2.95. 2.96 then. Now, whoa, 2.96. Now, what do we call that? Well, we're going to write the lowercase letter m to stand for molality. But just like the word molarity, which we called a molar solution, we're going to call this a molal solution. Weird word, I know, but that's what it is. So it'd be a 2.96 molal solution.
2.96 molal.
That's exactly it. Yeah, that's a weird one. Okay, some of you look like you're about ready to wrap up. That's unfortunate because I have one more to do. All right, next one. And we can do all kinds of things with that molality, which we will do tomorrow. So I'm not too worried about giving you guys a bunch of examples yet. The last solution concentration that we're going to look at is percent by mass. Although sometimes we might also look at percent by volume. It depends on whether we're looking at solids dissolved in a liquid or liquids dissolved in liquid. Typically, with percent by mass, we're going to be talking about aqueous solution then dissolved in water. It's going to look like this. Sometimes we'll also call it mass percent. Doesn't really matter. We're going to take the mass of the solute and divide it by the mass of the solution. Now, what is the solution composed of? Solute plus solvent. And you just multiply by 100. The reason I broke it down like this, sometimes you're going to be asked to find what mass of solvent might be required to make a certain percent, in which case you'll know this, and if you know that, you know that, and you'll know that. So we can solve for this. That's why I wrote it down. Okay? Pretty straightforward. Example number, gosh, I think it's 4. Determine the mass percent or percent by mass, doesn't matter which way you call it, of a solution prepared by dissolving 27.86 grams of barium chloride in 150 milliliters of water. Well, it's basically just a matter of plugging and chugging. We have the mass of our solute, 27.86 grams of barium chloride. What is the mass of our solution? Well, that's a volume, but as we know, it's water, so its density is 1. Hold on. So it's 150 grams of solvent plus 27.86. So it's 27.86 grams of solute plus 150 grams of solvent. And just multiply by 100. All right, here's the deal. I have every assignment for chapters 12 and 13 already online, and the answers and solutions to them. Everything's on there already. You just need to do them. I've got both 1 and 2 on here. I'll leave some here for you guys to grab. I'll leave some over here for you guys to grab.